Okay. So as I mentioned to you last time, today we are going to start on a new topic. Are you able to see my screen?
Yes, sir.
Yes, sir.
Okay, good. So we are going to embark on this topic of channel coding. We'll first take a look at the block diagrams, and we'll motivate the topic of channel coding, what it is and what is the big idea. Then we'll look at some practical schemes, similar to Huffman coding and Lempelzil coding. For channel coding also, there are several schemes that are actually implemented. Radio, whether it is a cell phone or your satellite TV or anything. And then we'll get into some conceptual aspects of channel coding. One topic will be Hamming distance, and the other topic will be based on linear algebra that you have learned in your high school math. So this will be a kind of a nice application of some of the mathematical topics that you have learned. And then we are going to look at an aspect of channel coding which is very relevant in today's world in 5G systems and in the future generation. This iterative decoding is gaining a lot of importance. And it's a very elegant, very nice technique that also is very easy to understand. Okay, so that will go over. That will lead us to what are known as low density parity check codes, or LDPC in short. So LDPC codes are going to be part of the 5G standard. And learn about this coding techniques. Now, topic number 8 is some miscellaneous topics. I don't know whether we will cover them or not, depending on how much time we take. In topic number 1 to 7, we may or we may not cover topic number 8. Then topic 9 is a visual explanation. So that also is something that we may or may not get to. Okay, so with that, let us look at the block diagrams similar to the ones that we looked at the start of channel source coding topic. So this is the overall diagram of a digital communication system. Okay, when we go to modulation, there I will also put a diagram of an analog communication system. It's actually very simple. All that it has is just the modulation and demodulation. It doesn't have any of these other blocks. But for a digital communication system, this is a representative diagram. This is also called the physical layer. Okay? The actual digital communication system has multiple layers. It's like the layers of an onion. So this physical layer is considered to be the heart of the digital communication system. This is what pumps the blood, so to speak. And then the upper layers, the data link layers, or the network layer, or the TCP/IP layer, or the application layer, etc. Those are like management type of layers. They kind of control the flow of the data over the internet. I don't believe that we'll be looking at those upper layers in this course. Or maybe towards the very end, I'll give you kind of a very brief preview of those upper layers. But you will learn extensively about these higher layers in a future course that you'll be doing on computer networks. Okay. So in that computer networks course, this physical layer, whose block diagram is shown here, will be not as much emphasized. There, the focus will be on the upper layers. Whereas in this course, we are looking at the blood vessels of any communication system. And that is the physical layer, and that is what I have drawn over here. So this source encoding is kind of part of the physical layer. Sometimes it is also part of the application layer, the topmost layer. And that is what we have already studied. So now we are going to go to channel coding. We will not cover encryption and decryption. Again, that is a separate course in itself. But by the way, even the channel coding is a separate course in itself. Source coding is also a separate course. But encryption and decryption definitely is a kind of a maybe a little bit unrelated to our overall flow. So we will not at all cover that topic at all here. But again, there you can take a course on encryption, secrecy, network level secrecy, or network level data protection, and so on. So encryption is something that you all are familiar with. Now if you start your computer, Microsoft has its own security protocols, and you can actually download some software which will provide protection against viruses or malwares or phishing attacks and all that. So this encryption and decryption is like providing you secrecy, providing you privacy. Today if you use WhatsApp, even when you start a new chat, you get a message saying that your data is fully encrypted. Your messages are fully encrypted. Even Facebook or WhatsApp can also not see what you are sending. So that is what the encryption does. Over here at DICT, we have some professors who are expert in this topic of network level secrecy. Professor Manik Lal Das, Professor Anish Mathuria. So maybe you will learn the topic of encryption and decryption from these professors later on. Channel coding is also actually, we have many experts of channel coding. Professor Manish Gupta actually teaches a course on channel coding. Professor Gagan Garg is also very knowledgeable about channel coding. Who else? I can't recall the names, but I think there are several other professors who are also working on channel coding, meaning that this is their bread and butter. They think of channel coding all throughout. This is their research problem. They have students working full-time on the topic of channel coding, and they develop research thesis and all that. So this is the topic that we are going to study. We will see that unlike source coding, we will probably spend a little more time, okay? This is about 128 slides. So I don't think we can finish this topic of channel coding in just few lectures. Maybe we will take at least 5 lectures or 6 lectures. Okay, so let us begin. So what is channel coding? Sometimes, by the way, it is also known as forward error correction coding, meaning that forward error correction means it's happening in the forward direction from the transmitter to the receiver. There is no feedback coming back from the receiver to the transmitter. That would be called return feedback error correction coding. By the way, that also is implemented, but that you will learn in your computer networks course, that feedback-based error control or error correction is implemented at higher layers, data link layers, for example. That is not part of what is known as channel coding or the FEC. Purpose of the channel coding is to turn a noisy channel, which obviously can introduce errors, into a noiseless channel. And it's obvious why this is very important function, because today when you talk on the phone, many times your call gets dropped or you get a lot of disturbances. Sometimes when you are watching video, the video starts buffering, and so on. So that is happening because the noise kind of overpowers the signal. at the receiver. More specific example is that in the 5G and the future generation systems, as we have seen in the first lecture or initial lectures, there is a plan to do to allow remote surgery. Okay, so now think of this, that a surgeon is operating but remote. And remote operation again is possible only through a communication link. And if that communication link is noisy, then the patient is in trouble, because the surgeon is moving his instrument or her instrument in a specific manner, but then the actual robotic arm, maybe inside the body of the patient, doesn't follow the surgeon's movement, and then it can actually be highly damaging. So this in the 5G service, there is a part of service which is called ultra reliable service, UR, short for ultra reliable. And that reliability, meaning turning a noisy channel into effectively a noiseless channel, is something that channel coding can do. Now, the real world channels are always noisy. So that is what the channel coding does. It turns a noisy channel into an ideal channel, as close to noiseless channel as possible. Now, at this point, you may ask that why do I say that the real world channels are always noisy? Maybe there are some cases when there is not a whole lot of noise, right? I mean, sometimes you are in a party and you're trying to hold conversation with your friend, and that is very difficult because there is a lot of noise. Maybe a loudspeaker is playing, and maybe there are a lot of people nearby talking, and so that is a case of a noisy channel. But then in some other cases, you and your friend are alone in a room and there is no noise. So yes, it is possible that even the real world channel doesn't have a whole lot of noise. So then why do I say that real world channels are always noisy? Well, the reason is that, as you have seen again in the initial lectures and what you did in the very first lab, the noise introduced by the channel, first of all, how it is measured, who remembers that? What is the metric for measuring the noise in a real world channel?
Conditional probability, entropy.
Voltage
What did you do in the first lab?
or power.
Power of
get
noise.
SNR
Correct.
S
So,
noise.
so the way that you measure the noise at the receiver is through the received noise power, which we had called P of n. So when we say that some channel is highly noisy, it means P of n at the receiver is very high. Some channel is not as much noisy, P of n is very small. But you see, what you had observed in the first lab is that P of n by itself doesn't mean much. What actually drives the performance of a communication system is not the absolute value of P of n. Instead, it is
SNR.
SNR. It is the power of noise relative to the power of signal. So maybe there are some real world channels for which P of n is very small, right? But then in that case, what it means is that the signal power P of s received at the receiver, we can reduce it. And maybe that will definitely reduce the SNR, but the benefit we will get is that we will have to transmit less power from the transmitter. And that is very important. That is a big benefit. I'll give an example of a satellite link. Satellites are like 35,000 kilometers away from the Earth. And therefore, if you happen to be nearby ISRO in Jodhpur, Tekra, you will see that ISRO campus has huge antennas, big dishes. Those antennas actually make sure that although the satellite is that far away, P of S at the satellite receiver is sufficient enough so that the desired PS over PN SNR is maintained. Now, if it so happens that P of N is small, then the ISRO engineers don't have to worry as much about making sure that P of S is as high. They can maybe reduce the size of the antenna. Maybe they can reduce the power amplifier specifications. And so it translates to real benefit in terms of an engineering design. So that is why all the real world channels are noisy. In case if some real world channel is completely noiseless in terms of, let's say, PS over PN is really high, then actually that is not a very good design. That means that transmitter is wasting the transmitted power. Transmitter can reduce the power and gain benefit in terms of maybe a reduced antenna size, a less expensive amplifier, and so on. So the channel coding takes an actual physical channel which has maybe not as high an SNR. Maybe it's not completely noiseless in terms of SNR. SNR is probably not infinity. SNR is more like maybe 10 or 20 in terms of the ratio. And then, surprisingly, magically almost, it turns that channel with SNR of, let's say, maybe 20, it turns that channel into an effective channel whose SNR is maybe 2000. Without any change in what the transmitter is doing. We don't ask the transmitter to send more power. It's all by clever algorithms. Okay. So at first it might appear that, how can you do that? The channel has already introduced the noise. So how its effect can be undone? How can you make a channel which is noisy, how can you make it noiseless? So for that, we go back to our Bayesian belief model, cause versus effect. And there we have seen that the reason why the receiver makes error is because when it, let's say it's a binary channel, then when it observes y equal to 0 at the channel output, it cannot decide with certainty whether the cause is x equal to 0 or x equal to 1. Right? So if I get y equal to 0, it could be that it's sender sent bit 0, or because of this red arrow, it could also be that sender sent x equal to 1. This is the reason why the receiver can make errors, bit errors. The receiver will employ the Bayesian rule, maybe maximum likelihood or maximum a posteriori method, but that will just make sure that the errors become minimum. If you don't use those techniques, then the errors can increase. That is what you are learning or what you are experimenting or what you have experimented in the previous lab 5. But even if you have Bayesian technique implemented at the receiver, there will be errors. That is happening because the receiver cannot be certain. If P is equal to 0, then there will not be any errors. Whenever the receiver gets y equal to 0, it tells with certainty that x is equal to 0. But because p is not 0, the receiver will make errors. Okay, so if I want to convey the main idea of channel coding in a very simple manner, it is that we take that Bayesian diagram and we kind of modify it. How do we modify it? So we don't change the transmitted symbols. If it is a binary source, then it generates x is equal to 0 and x equal to 1. It generates bits. But somehow, the receiver, we increase the number of different distinct symbols that the receiver can get. So if I draw a diagram of an ideal channel coding scheme, then it would look like this. Right, so the transmitter symbols are still zeros and ones, but at the receiver, I have now 4 symbols. And somehow I make sure that when the transmitter sends x equal to 0, the receiver can get only the upper 2 symbols. And when the transmitter sends x equal to 1, the receiver gets only the bottom 2 symbols. Now with this, I claim that the probability of error becomes 0. The receiver never makes any errors. Why is that?
The first bit will always correspond to the bit sent. X equal to 0, then y equal to 0, 0 or 0, 1.
Okay. Yeah. Who can give me some alternate way of answering this question?
There is no collision between the bits which are received, so transmitter can decide.
The transmitter can decide?
Sorry, receiver. Sorry.
What did you say? Can you repeat again?
Means the bits which are received at the receiver end, there is no collision between the bits. Means 0, 0 and 0, 1. If a receiver is receiving 0, 0 or 0, 1, it can decide that okay, x is equal to 0 is transmitted, because 0, 1 or and 0, 0 are not transmitted by x is equal to 1. So
Correct. Who can give a little bit more mathematical answer? Maybe in terms of conditional probability or conditional entropy, like that. What is the conditional probability of x given y in this case?
so it will be always be 1, means for a particular
Either
value of
0
x.
or 1.
Right. So in case if you get y equal to 0, 0 or 0, 1, then the conditional probability of x equal to 0 becomes 1. The conditional probability of x equal to 1 becomes 0. And such a variable has conditional entropy of how many bits?
0 bits.
Very good. So Taran said it correctly. So conditional entropy of x given y becomes 0. And similarly, if you get 1, 0 or 1, 1, then probability of x equal to 1 given that y becomes 1 and x equal to 0 becomes 0. So again, you get conditional probability numbers which are either 1 or 0, and therefore if you do this, if you take the odds either in favor of 1 or in favor of 0, you get an answer which is either infinity or 0, which means that the receiver does not have any confusion, it doesn't have any doubt about what bit was transmitted. So this is the main idea of channel coding. Now, how can this be done? Or something like this. And by the way, I'm not...
Bayesian propagation method, repeating the test.
Harsh, yes, Harsh, you are correct again. This can be done, one way to do this, or something like this, maybe not the best ideal way that I have shown it here, but sort of, we kind of see that something like this is happening if we use what type of coding? Repeat by encoding, right? So with that repeat by encoding, diagram that we get looks like this. Right now I have used it for n equal to 3, but I can draw it for any other value of n. So the transmitter still sends 0 and 1, but then channel coding repeats it 3 times in this case, and so you get a total of 8 different ways that the receiver can observe y. And what will happen is that when x is equal to 0, and this you have done in one of your labs, the probability of y equal to 0, 0, 0 is going to be the highest. And then the next highest will be the probability of y taking these 3 other values. So these 4 arrows are going to be the strongest. Okay, by the way, this green will be the strongest, and then second will be these 3 red arrows, which will have the same strength in terms of probability. But unfortunately, there will be still some leakage. You know, this probability of conditional probability of x, likelihood of y equal to 1, 0, 0, given x equal to 0 is not going to be 0, like what I had drawn on the previous slide, which was the ideal case. That's why I have drawn this thin gray lines. But hopefully the probabilities corresponding to these gray lines are much smaller than the actual P of the binary symmetric channel. And so therefore you get improvement in terms of bit error rate or in terms of probability of making error. Yeah.
Sir, please, one slide go back, please. Sir, while doing our labs, we had repeat by 3 coding. Sir, in our labs, we had 1, 0, 0 corresponding to x equals to 0, not x equals to 1. Because 0 is coming twice.
Good,
so
good point. Yeah, good point. Very good point. So this, thank you. I think, who said this? Krupal, right?
Yes, sir.
So this should be y equal to 1, 0, 0. And this should be y equal to, what should I write here?
0, 1, 1.
0, 1, 1. Great. Good, Krupal. Your sharp eyes. Okay. So So this is good. We are able to reduce the error probability, but there is a cost associated with this. Who can tell me what do we give up? I mean, this reduction of the probability doesn't come free of cost.
We need more storage.
Need either more storage if you are
We need
doing
to send more number of bits, so more.
right.
If
If you are storing it on a DVD or CD player or your USB drive, then that USB drive will have to be 3 times bigger, which is obviously more expensive, right? If you purchase 3 USB drives, it will cost you 3 times more than if you just can get away by using one. Or if you have data subscription of your 4G provider, then you will be consuming 3 times as much data, which also is going to increase your monthly bill. More technically, we are making use of the channel 3 times, but actually sending only 1 bit of information. We send 3 encoded bits, but I mean either 111 or 000, but actually those other 2 bits are repetitive. They are redundant. So I should say that the other 2 bits
Sir, will this repeat by n scheme will also work for n is equal to 2?
it will work, but not as well.
Yeah, because 1 0 and 0 1 have same probability.
Exactly. And typically in repeat by n is kept to be an odd number. And the reason is that if you keep n to be an even number, you will end up with this type of case that 1 0 and 0 1 has same probability. And so if you get one of such y values, then x equal to 0 and x equal to 1 are both equally likely. So you get slight benefit if you, instead of using n even, you make n to be odd. Okay, so this concept of redundancy, meaning that we are sending more bits than actually necessary, does it remind you of something?
Source coding.
Source coding, exactly, right. So in source coding, the objective is to squeeze out the redundancy. Whereas channel coding does exactly the opposite. It puts extra redundancy. So you may ask that then what is the point? Source coding does all the hard work in removing the redundant bits, but then channel coding goes ahead and puts those bits back up again. And then what do we get? Is it not like you take 280-degree turns and then you're back to where you started? So the answer is no, obviously, right? I mean, if that was the case, today's communication systems would not have source coding and channel coding back to back. So why is that answer no? We'll come to that later on. Now we are going to define this rate of channel coding scheme, which is the ratio k divided by n, where k is the number of information bits. For the repeat by n, information bit is always 1, right? We just take one information bit at a time. We repeat it by n times. Capital N is the number of encoded bits. This rate is always between 0 to 1, and this is small r. So for repeat by n coding, the rate is 1 over n, right? Because we have one information bit which we are repeating n times. So what I think you may have observed in your lab number, I think it was 3 or 4, I don't remember, that the error probability can be reduced, meaning that, you know, these two sets that we had over here, they can be made almost non-overlapping, meaning these gray lines can be almost made to disappear if I keep on increasing n. But the price paid is that when I keep on increasing n, the rate becomes increasingly closer to 0. So we'll take some numerical examples next, but before we do that, I'll take a quick break. Okay, so let us look at the error probability of repeat by encoding, and we'll start with this, I think, repeat by 3 coding when for a particular value of the binary symmetric channel error probability small p. You know, this is a problem that I think you have solved in your lab, but let us go over it one more time. So for repeat by 3 coding, what we have observed is that the receiver uses majority voting. And in that majority voting, the answer comes out wrong if either 2 bits are in error or all 3 bits are in error. And the way that it can happen, 2 bits can be in error when you're transmitting 3 bits. 3 choose 2 times. The probability of each sequence is p squared times 1 minus p. So there are 3 ways that you can have 2 bits in error. And the probability of that is p squared times 1 minus p. So that is actually same as the probability of these 3 lines, these 3 gray lines. It is p squared times 1 minus p, and there are 3 such lines as shown here. And then the last line is this 3 choose 1. Sorry, this should be not 3 choose 1. Sorry, it's a mistake. What it should be here?
3.
3.
3 choose 3. Yes.
Sorry, 3.
And so the 3 choose 3 is 1, and the corresponding probability is p cubed. So you get this final answer. So if the symmetric channel is introducing 10% errors, then the repeat by 3 reduces to only 3%, roughly. Okay, that's a real gain. I mean, 10% becomes 3%. You get a benefit. But suppose now if I want to reduce it further, I say that 3% is not acceptable to me. I want 0.3% or 0.0003%. Then you have to use higher value of n. And for the higher value of n, this formula here generalizes to this formula. So all we are doing is we are evaluating the binomial PMF and adding the right hand side half of the PMF from n plus 1 divided by 2 up to n. We are just adding the corresponding PMF values. It's just a generalization of formula that we have for this case. Now this is something that we can easily program in MATLAB, and then I can see what happens for higher values of n. So that is what I have done here. Right, so p is equal to 10%. So if I don't do any coding, n is equal to 1, then obviously I'll have to live with 10% errors. If I do repeat by 3 coding, my rate became 1/3, but I got an error rate which is only 3% now. If I do repeat by 5, then 1/5 is 0.2. So rate went down, but the error rate also went down. And so on. If I do repeat by 7, repeat by 9, repeat by 11, I start getting values which become closer and closer to 0, but then the rate also starts dropping. So this part is little too compressed, too dense. So the way to look at this in a more microscopic manner is to turn the y-axis into logarithmic scale. And so in logarithmic scale, we can better observe what is happening. So you will see that rate 1/5, this is the error rate. If I want 10 to the power minus 5 error rate, then I better have repetition of, so this is 3, 5, 7, 9, 11, 13, 15, and 17. So if I want error rate less than 10 to the power minus 5, then my n value should at least be about 19. If I repeat each bit 19 times, then I will get really a super improvement in the error rate. P will become less than 10 to the power minus 5. Suppose if it's a very highly precise requirement, like that remote surgery or something, where I wanted error rate of 10 to the power minus 15, meaning that when the transmitter sends 10 to the power 15 bits, which is what comes after trillion. Trillion is 10 to the power 12, and then, I don't know, zillion or something. The transmitter sends those many bits, then it gets only one bit in error out of those many bits. So that portion of the graph is plotted here. I have zoomed in. So you'll see that if I want a very precise, very highly reliable channel whose effective error rate is 10 to the power minus 15, my code rate better become like 0.016 or 0.070. So that is what I have written here. But when R is 0.016, 1 over R, which is equal to N for this repetition rate, becomes about little more than 60. Which means that I have to repeat each bit 60 plus times, maybe 63 times. So going back to our USB example, if I have a requirement of, let's say, 1 gigabyte, then if that USB drive is faulty and it introduces 10% errors, then instead of buying 1 gigabyte memory, I will have to buy 63 gigabyte memory. You can go and look at Amazon.com and you'll see that there'll be a huge price difference. In terms of communication system, you are not storing, but you are also transmitting, then this reduced rate translates to a bandwidth increase. Your bandwidth requirement just explodes. Why is that? I think we'll talk about it soon. Okay. So now I'm going to ask you some questions. Okay? So participate. Think you know the answer? Don't be silent. Let us see. Maybe I should do a poll. If I do a poll, then everybody has to answer because your poll results come to me. So I will know who has not answered. Should I do the poll or should I leave it? Let me not do the poll, but push yourself, okay? Don't be silent. If you don't want to speak, you can obviously write your answer in the chat window. So we are going to assume this BSC channel that we all are familiar with now. We are assuming that there'll be certain value of P, the crossover probability, And we are going to also assume that this value of P is known both at the sender and the receiver, the sink, the source and the sink of the information. They both know the value of P. You may ask, how is that possible? Well, there are some engineering designs by which this value of P is approximately known. Okay, I mean, we are not going to get into that part of the communication system engineering, but this the value of P can be known somehow. In the real world example, for the disease problem, the value of P is also known because the manufacturer of the test instrument would have done some calibration or some measurements before selling that instrument, and so when somebody buys the instrument, that laboratory equipment, it will come with a user's guide, and that user guide will say that this is the value of P, right? So somehow or other P is known. How it is known, we won't get into, but let us assume that it is known. So my first question is going to be simple. That let us say that first of all that the transmitter is sending zeros and ones with equal probability. And it is sending, let's say, maybe 1,000 bits per second, right? And the P value is 0. Then what is the rate at which the information gets received?
Thousand bits per second only.
Okay, why do I get only one answer?
1000.
1000 bits per second.
Yes, sir. It should be 1000 bits per second.
1000 bits.
Yeah.
1000 bits per second.
Yeah, so that is the right answer. So because P is 0, there are no bits in error. We get everything that the sender is sending. You get 1000 bits per second. Okay, so this was probably a simpler one. Yeah, correct, Kirtan, it is 1000. But now let us consider this question that now suppose P is equal to 10%. So now what is the rate at which the information is?
90 bits per second.
No, P is 10%.
Half is same.
900 bits.
Sir, it will be same as 1000 bits per second.
Yes, sir.
So most of you, like Pinak is saying 1000, Aditya is saying 110 bits. Sanket is saying 900, Rakshasya is saying 900, Divya is saying 1000. Wow. Okay. Divya is brave. Why Divya, you went against the flow? Most of you are saying 900. Why did Divya say 1000 bits per second? Divya, you can speak out.
Sir, information will be received, but it would be wrong information. So
Wrong information is no. You can't say that. Even if you receive wrong information, you have received information. I mean, obviously, only the bits that we received correctly can be said as having been received. Right? I mean, so when I say the rate at which the information is received, what obviously it means is that the information which is usable. If you throw junk information and you still say that it is received information, that is not the right thing. So if you want to just look at how many bits per second the receiver gets correctly without any errors, then obviously the answer cannot be 1000, right? Because the channel is randomly flipping about 10% of the transmitted bits. So yeah, so I think majority of you said that it is going to be 900 bits per second because channel is messing up with about 10% of the bits, right? Ayush, right? Om is saying 1100 bits per second. Now, wow, that is really, really ambitious. you are transmitting 1000 bits. How can the receiver get 1100 bits? You haven't even transmitted 1100 bits. So then, can you explain why you would get 1100? It's an interesting answer, but it is a wrong answer. Interesting, but wrong. So I want to understand what made you think that the receiver will get 1100 bits. Speak out, please. Why will the receiver get 1100 when the transmitter is sending only 1000? And in addition, the channel is flipping 10% of those 1000 on average. Okay, why are you silent now? You have to explain what made you think it's going to be 1100. Okay, fine, if you don't want to speak out. But yeah, so I think majority of you, maybe 90% of you said that it is going to be 900 bits per second, maybe 0.1 times all of you, 10% of you said it's going to be something else. But so let's go by the majority, right? So the received number of bits is going to be 900 bits per second. So now I'm going to ask you another question. And you have to use the same logic, okay? Now you can't change the logic. Use the same logic and tell me that for what value of P will the information transfer, the rate of information transfer will become 0, meaning the receiver won't be able to get any.
0.5.
1.
So,
It should be 0.5.
1.
so everybody is saying 1, right? And that is good. You are using the same logic. You said that when P is 10%, I have to remove 10% of the bits. So 1000 becomes 900. So when does 1000 become 0? Well, you remove 100% of the bits. But Ayush said 0.5. That is an interesting answer. Now, remember, I had mentioned this very clearly that we will assume that the value of P is known. So think about your answer. If you say that when P is equal to 1, the rate of information transfer becomes 0, then does it make sense to you? When P is equal to 1 and the receiver knows that P is equal to 1, then
Sir, if receiver knows is equal to 1, then we can easily deduce that if y is equal to 0, then we can decide that x equal to 1. And
very true. And then so the answer that you gave is the answer that I had predicted you would give. So that is what I've written here, that the information transfer becomes 0 when P is equal to 1, but it cannot be right because when P is equal to 1, the BSC stops being random. 100% of the time it will flip each bit without any fail. It becomes very deterministic actually. So all that receiver has to do is like what Vandan said, it will just flip each received bit back. And so it will get all of the 1000 bits without any error. And so then you have to start stretching your head because you use the same logic to answer question 1. And that also I had guessed correctly that you would say it will be 900 bits per second, but that cannot be right either because if this was right, then the answer to question 2 would have been right. But more specifically, you can't say that receiver will get 900 bits per second because the transmitter is messing up with some 10% of the bits because yes, the receiver knows the value of P. It knows that 10% of bits are in error, But how it can get remaining 900 bits every second? Because it doesn't know which of those 100 bits are getting flipped. Right? So it doesn't know it got flipped and which came out okay. So that is why 900 bits cannot be right. So this answer is 900 bits per second, or the information rate becomes 0 when p is equal to 1. Those were based on our guesswork. We have seen that they don't come out right. So could it be that if we answer these questions using the math of information transfer that we have studied, the results are more satisfactory? Let us look at that. So we will again answer question 2 first. And actually, somebody did say that for question 2, the answer is p equal to 0.5, not 1. So that is actually the right answer. But so see what happens when p is equal to 0.5. So I'm going to go through some math. I'll just quickly flip the slides. Later on, you can study the math if you wish, or you can do this math on your own very easily. But the answer will be that when p is equal to 0.5, the conditional probability of x given y remains the same as the actual probability of x, the marginal probability of x. So this is the answer that I'm already giving. Why this is the case is what I'll be deriving next, but I won't spend too much time on it. This is the main thing. When p is equal to 0.5, conditional probability of x given y, the posterior on x remains the same as the prior. We have used a specific wording for this type of variables. Who can tell me?
Independent.
Very true. Very true. This means that x and y are independent. The output of the BSC becomes independent of the transmitted x when p is equal to 0.5. And it doesn't matter what the p of x is. Remember, for p of x, we have used q and 1 minus q. It doesn't matter. So why is this the case? Well, the proof is here. Okay, I won't explain the proof. But the main idea is that when this BSC is introducing 50% errors, then the marginal on y becomes 50% also. Y equal to 0 and y equal to 1 both are 50%. And therefore, the posterior on x, in the numerator you have 50% from the BSC channel. The denominator also is 50%. So that 0.5 cancels out and you are left with the prior on x. This is for the case when x and y both are 0. But the same math can be shown for the remaining 3 cases. And therefore, we say that the conditional probability of x given y is same as probability of x. But then that means that conditional entropy also remains the same. So that is how we have defined conditional entropy. It is just the function of p of x given y. But then when conditional entropy remains the same as the entropy of x, what happens to the information transfer?
Becomes 0.
Because it's the difference between the two. If both are the same, then the difference becomes 0. And therefore, we can't get any bits through. So the rate of information transfer drops from 1000 bits per second to 0, not when p is equal to 1, but when p is equal to 50%. And it makes some intuitive sense, right? We have said that y and x are independent. So if y is independent of x, then how can transmitter send something with the aim of influencing the receiver? If you think of it as a process of a coin, then what happens when p is equal to 0 is that the transmitter tosses a coin, and at the receiver sees exactly the same toss. So whenever the transmitter toss of a coin lands on heads, the receiver always also lands on heads. And the transmitter coin lands on tails, the receiver always ends on tails. They are like completely connected. That is one extreme. This is the other extreme, that the transmitter is tossing the coin, and the receiver, it is completely independently tossing its own coin. Then what is the importance of transmitter? You don't need a transmitter in that case. The receiver can just independently toss its own coin. And if you don't need a transmitter, then how can you say that you are conveying any information? Does this make sense?
Yes, sir.
Okay, good. So at least intuitively, logically, p equal to 0.5 appears to be the right answer for question 2. What about question 1? Well, again, I'm going to give the answer first and then go to the derivation. So it turns out that for BSC P, for any value of P, the conditional entropy is given as this binary entropy function, which you are familiar with. By the way, there is a missing bracket here, so for that. Okay. So why is this the case? Well, again, even in this case, in this case, it is the same thing happening, that the marginal of y remains 50%, but for a different reason. And so now what happens is that, again, the numerator, which is the prior, and the evidence, which is the denominator, they cancel out because they both are 50%. And then what you are left with is 1 minus p for this case, or p for the other case. When y is equal to 0, probability of x equal to 0 just becomes 1 minus p. Probability of x equal to 1 remains p. So what we have proven is that when y is equal to 0 is received, the information source becomes a Bernoulli p random variable instead of Bernoulli q equal to 0.5 random variable, which is what we have assumed in this case. The same way, when you get y equal to 1, again, you can use the same math to see that. Even for that case, the information source becomes Bernoulli p random variable. Therefore, the conditional entropy is nothing but the binary entropy function. So now what can you say about the information transfer in general? Information transfer will be so it will remember entropy of x is 1 bit because we have taken q to be 0.5. And so information transfer simply becomes 1 minus binary entropy function. So remember, binary entropy function was that parabolic shape. So we flip it and then we add 1 to it. So it becomes like a mirror image of it. So this is what we get. And so as expected, when p is equal to 0.5, the information transfer becomes 0. And the other question that we had, what is the value when p is equal to 0.1? We just look up over here. It's about little more than 0.5. So with p equal to 0.1, we can transfer the information at a rate of not 900 bits per second. It is not that high, but about 530 bits per second. And if we transmit at this rate, at the rate of 0.53, then what Shannon showed is that the error probability can be arbitrarily reduced. Not 10 to the power minus 15 or 10 to the power minus 100 or 10 to the power minus 1000. Can be reduced as low as you want. And the rate doesn't have to drop below 0.53. That is the amazing part. We don't need error rate to become 0, means rate becomes 0. Remember, we saw earlier that even to get 10 to the power minus 15, R had to drop to 1 over 63 or something. And so the chart looks like this. This red is the information transfer. And that is little more than 0.5. This blue is the repetition code. And so you see the advantage, right? Instead of repeating a bit 63 times, instead of buying a memory which is 63 times as larger, you need to buy a memory which is maybe just twice as big. So that is the magic of channel pooling. Okay, so we'll end today's lecture here.